Okay guys, you're most welcome in my class. This is Dr. Sushmita Yadav and today's topic is the carbocation. Guys, carbocation is a very common topic and important in all the entrance exams, even though the direct questions over this topic has been found every year. So without wasting time, let's discuss. In this lecture, we will discuss about the structure, stability and rearrangement of carbocation, means A to Z, everything about the carbocations. So first of all, I am taking here structure of carbocation. Structure of carbocation. So first of all, how the carbocation are formed? Carbocation are formed by heterolytic fission of a polar bond in which carbon is less electronegative in comparison to another atom. For example, this is a molecule in which X is some highly electronegative atom. So what will happen in this heterolytic fission? X will take up the both bonding pair of electron. As a result, the positive charge will come over the carbon and negative charge will be there. So that positively charged carbon is called carbocation. Okay, so carbocation is nothing but the positively charged carbon. Now, how the structure of carbocation it is having. So, if we discuss here carbocation, you can see it is forming how many covalent bond or sigma bond? One bond with the carbon and two bond with the hydrogen. So, a carbocation always form 3 sigma bond and 1 positive charge. This positive charge reflects that the carbocation is having a unhybridized p orbital. This p orbital is unhybridized empty p orbital. Okay, so what is the structure of carbocation? Carbocation has the 3 bonded electrons pairs and 1 empty orbital, which is the pure p orbital, unhybridized orbital. So if we list out all the characteristics of a carbocation, we can list out here that carbocation is sp2 hybridized. What is the hybridization? With the 3 bonding pair or 3 sigma bond, it will be sp2 hybrid in nature. And sp2 hybrid means what will be the shape? Shape will be trigonal planar, because this p orbital is not going to disturb your shape. It will be having a shape of trigonal planar and definitely with 1 p orbital. Now, the carbocation is having how many valence electron? This is also a question. So if you will check here, there are the 3 sigma bond and each bond have 1 bond pair. So total 3 bond pairs are there. That means a total of 6 valence electron. 6 valence electrons a carbocation have over that positively charged carbon. Okay, now with the 6 valence electron, it is considered as electron deficient in nature because of not having a complete octet. So it is electron deficient in nature. That's why carbocation have tendency to gain electron from some donor atom, and because of having strong tendency to react or to get electron from others, they are highly reactive. They are highly reactive and short-lived. Means as soon as they will be formed into the reaction, they will consume up and will give you the product. That's why they are called the reaction intermediate. So many mechanisms you will find over the carbocation. So this is all about the structure of carbocation. Now second point we will take here, stability of carbocation. So guys, be very logical, because carbocation means something electron deficient. Okay, carbocation means a carbon which is electron deficient. So if some group, atom or any property is there in the molecule which is going to give electron to the carbon to compensate its electron deficiency, then it will stabilize the carbocation. And similarly, if some group or atoms present in the molecule which are going to withdraw electron or snatch electron from the carbocation, so that will destabilize carbocation. So here we can summarize the thing in 2 points, that presence of presence of EWG group. EWG group means electron withdrawing group. If EWG group increases, means something which is taking up electron from carbocation, and carbocation is already deficient. So stability, these kind of group will decrease the stability of carbocation. Carbocation stability decreases. Okay. Similarly, if we are having some ERG group, presence of ERG group. ERG group means electron releasing group. If there are some electron releasing group, they will give electron to the carbocation and will enhance or will increase the stability of carbocation. So this is something basic you must remember always. It will increase the stability of carbocation. Now I'll unfold this portion also. EWG group. Which group are considered as EWG group? Any minus I group or minus M group will be considered as EWG group. Okay? In which they will take up electron from molecule or carbocation. Now, ERG group means any plus factor, either plus I, either plus hyperconjugation, either resonance. Resonance is always a plus factor. Okay, either resonance or either plus M. All these factors are the stabilizing factors. Okay, let's take one example here. For example, we are having CH2 double bond CH. And here again CH2 positive. And second example is like this. So you can see clearly which factor is working here. There is the resonance. Resonance, this is double single carbocation. Double single positive is a conjugation. Double single positive charge. It is a conjugation. So there is the conjugation means resonance will work here and you can form the two resonating structure of that. Okay. In this case, there is no resonance. It is a saturated molecule, no conjugation, only the plus I factor. Now one question is there. There are both the plus factor are there. Means resonance is there, plus I is there. Now how to decide which is more stable? So I am giving you a order here. For the carbocation, plus M increases the stability very much. Then your plus R means resonance, then hyperconjugation, and then last is the plus I. Means plus I is the weakest stabilizing factor and resonance is quite more stronger stabilizing factor. So definitely this will be more stable than this. So this is a kind of example in which we are comparing the stability. Let's see some more examples for that. Okay. Okay guys, let's see all the examples one by one. Okay, in first one, they all are the alkyl group, no plus M effect is there. So only the hyperconjugation we will compare. So with respect to this carbocation, there are the 3 alpha hydrogen and each one of them is having 3 hydrogens. So total 3 alpha carbon are there and 9 hydrogens. So 9 alpha hydrogen are there. There is how many alpha hydrogens? 6 alpha hydrogen. There is 3 alpha hydrogen and there is no alpha hydrogen. And also nature wise we could write, because you guys have learned a very common example, tertiary carbocation more stable than secondary than primary. This is the reason why it is. By nature it is a tertiary carbocation. Second one is secondary carbocation. This one is primary carbocation and this one is also primary, or we call it super primary because only a single carbon. So if we check the stability wise, there is no 9 alpha hydrogen. So it will form a total of 9 hyperconjugative structure. Similarly 6, 3 and no hyperconjugative structure. And we know that hyperconjugation increases, stability increases. Okay, it is a stabilizing factor for carbocation. So stability of carbocation also increases. So this will be more stable than this. In this case, there are 3 alpha hydrogens, so 3 hyperconjugated structure, there is no one. Okay, so this is the order why the tertiary is more stable, because it is having 9 hyperconjugated structure, which is highly stable case. Okay, let's check here. This is also primary in nature, secondary in nature, and tertiary in nature. Moreover, you can check how many alpha hydrogen with respect to this carbon. This one is alpha carbon with 1 hydrogen. So there is 1 alpha hydrogen. With respect to this carbon, this and this is alpha. So how many hydrogen? 1 and 2. 3 alpha hydrogen. Then here, 3 alpha hydrogen at this, 2 here and 2 here. 3 plus 4, 7 alpha hydrogen. So we can see clearly this is again going to be more stable than this, tertiary more stable than secondary, than primary, either ring or either chain. If hyperconjugation we are checking. Now these two. Nature wise, this is secondary as well as this one is also secondary. So how to check? If we will carefully check, this positive charge is in conjugation with the benzene ring. Means it is a similar point like we are having this one. It is similarly like this. Like you can see, it is similarly like this. That means this positive charge will be a part of resonating system and will form how many resonating structure? 5 resonating structures. So there is a resonance with 5 resonating structure. While in the second one there is no conjugation. There is no conjugation. So only hyperconjugation we will take. Okay. And how many alpha H? 2 alpha H at this location, 2 alpha H at this location. Only 4 hyperconjugation. There are 5 resonance, there are 4 hyperconjugation, and resonance is more stabilizing factor than hyperconjugation, so this will be more stable. Likewise, here also, here this is secondary in nature and this is also secondary in nature. Now how to find out? Both are secondary in nature, so, and there is no resonance as well. So just check your hyperconjugation, because to compare the stability, we need to check the point of difference. Okay, how many alpha hydrogen are there? This is alpha and this is alpha. So 3 plus 2, 5 alpha hydrogen are there. With respect to this, okay, I draw the same structure. Okay, I'll change this. They are basically the same structure. Okay, I have changed that. In that case, this is alpha as well as this one is alpha. So how many alpha H? 4 alpha H. So with the 5 alpha H, definitely this secondary will be more stable than the another secondary. Okay, so likewise we will check the stability. Now, in this case, there is resonance. How many resonating structure? 5 resonating structure will be there. Correct? There will be total 5 resonating structure, 5 RS. Now here is also resonance. Double, single, positive. There is conjugation. But how many resonating structure will be there? Positive charge, if you want to count the resonating structure, just rotate the positive charge or the charge given at the alternate position. So first here, then second here, then third here, there will be 3 resonating structures. So only 3 RS. Now in this case, only 1 alpha hydrogen, no resonance. So we can check simply, this is highly stable, then this and then this. Now this is a very special case, or you can say it is a exceptional case. Why exceptional? Because in general, resonance dominate over hyperconjugation, because this molecule is having 9 alpha hydrogen and will show hyperconjugation. Okay, but this molecule is having resonance with 5 resonating structure, and generally it is found that in all the cases, resonance is more stabilizing factor than hyperconjugation. But this is a special case where the 9 alpha hydrogen, please write this in language. Benzyl carbocation is less stable than tertiary methyl carbocation. Tertiary carbocation having all the methyl group. Okay, so this is an exceptional case where 9 hyperconjugative structure are dominating over the 5 resonating structure. Okay, don't take it like if I change this one. Let's suppose instead of methyl, I am keeping one of them is ethyl. 2 methyl. Okay, I am writing 2 methyl and 1 ethyl. So now, how many alpha H? 8 alpha H. Then it will be less stable than benzyl. Correct? So only this is a special case where the 9 hyperconjugative structure are dominating over the resonance. So take it as an exception. Now, this one also. If you will see by nature, this is tertiary, this is secondary, and you will simply pick the example, this is more stable. No, that's not correct. It is not a normal tertiary because it is a bridgehead. If you will see the molecule, this is a bicyclo molecule in which you are having these 2 carbon which is connected through the bridge. Okay. If carbocation is having positive charge, means carbocation is present on bridgehead, it is a highly unstable condition, so you will not consider it like tertiary. Okay, so bridgehead, this is the bridgehead carbocation, highly unstable. And what is the reason of highly unstable nature? The reason is the Brett's law. The reason is the Brett's law. What the Brett's law states? Brett's law says that bridgehead cannot be sp2 hybridized because carbocation means which hybridization? sp2. So what the Brett rule says that bridgehead cannot be the sp2 hybridized until and unless your ring is 8-membered or bigger than that. So these are the few examples here. Who will be more stable? Definitely this one will be more stable with 3 alpha H. Okay, and it is highly unstable because of the bridgehead condition. Okay, so don't ever take all the example in the similar way. So this is also an exception case where you will have the bridgehead. So remember all this. Now we will discuss some of the very extraordinary highly stable carbocations, and in next lecture we will continue about the rearrangement of carbocation. Okay. Okay guys, let's see the examples. Extraordinary stable carbocation when some other specialization or other stability phenomena will be applicable. We know in the chemistry the most stable phenomena, most stable compound of stability according to the stability are the aromatic compound. So if your system having the carbocation is following aromaticity, then it will be highly stable. So rules of aromaticity, I hope you all remember that. Then we can discuss it like it is a 2-pi electron system and cyclic and conjugated. That's why aromatic. This is again 2-pi electron system because what is requirement of a molecule or ion to be aromatic? It should be cyclic, planar, have conjugation and follow the Huckel rule. It is cyclic, planar, have conjugation and follows the Huckel rule also. So aromatic system and highly stable carbocation. Now this is a carbanion I am writing. How many pi electron? 2 plus 2, 4 and 2 electron from this. So it is a 6 pi electron system and aromatic and highly stable anion, not carbocation, carbanion. Similarly, we have the carbocation. So because positive charge carbon is not having anything to donate to the system, it is deficient. So how many pi electron? 4 pi electron. 4 pi electrons are anti-aromatic if you remember. So it will be anti-aromatic and will be considered as unstable system. Or you can say they do not form generally. They are so unstable, they are highly unstable cases. Now this one, this is a 6 pi electron system having the conjugation, planarity and aromatic. This is called tropylium carbocation. Tropylium carbocation, and it is a very stable carbocation because it is a odd number of electron ring. So 2 time resonance, when you will do resonance, the positive charge will resonate 2 times over the ring and will provide extra stability to this. Okay, now if we compare between these two, this is aromatic system. Your positive charge is a part of aromatic system, so your positive charge is very much stable here. Okay, because if we remove the positive charge, your system is not at all aromatic. It is a normal cyclic compound, non-aromatic. So this positive charge is responsible for aromaticity here, means it is a part of aromatic system. But here it is having the 6 pi electron, aromatic, but this positive charge is not a part of resonance. Part of resonance or aromaticity. Okay, but in this is a part of aromaticity. Okay, so which one is more stable? Definitely this carbocation, because it is one of the part of your aromatic system, because without this positive your system cannot be aromatic. Okay, but here this positive charge is just put it here like the normal positive charge over the carbon. Aromaticity is not taking this charge into consideration because it is having a complete 6 pi electron system. So this positive is unstable. Now that means what we learned here, any kind of system which are having the aromaticity into them, all the carbocation system which are aromatic are highly stable. Now a very special case we will discuss here, CPM. What is the CPM? CPM is the cyclopropyl methyl carbocation. You can write down the name, cyclopropyl methyl carbocation. By nature, it is a primary carbocation in nature and there is no conjugation as well. So this should be less stable, or this should be a nominal or normal carbocation. But exceptionally, it is found highly stable carbocation. Let me tell you, because of the dancing resonance. I hope you heard that topic. Dancing resonance. So dancing resonance is found in CPM. In this CPM, basically, how would we explain that? We can explain in this CPM structure, if you will see carefully, there is a carbocation, means carbon with positive charge, and positively charged carbon have a p orbital unhybridized, and there is the sigma bond orbitals which are head-to-head overlap. Because of angle strain, because 3-membered ring are highly strained, so this bond will bend and will overlap or coordinate with the orbitals present at the carbocation, and this kind of conjugation is going to happen here. This is your carbocation. Okay, this is a kind of overlapping will occur here. As a result, you can show there is this kind of resonating structure and positive charge will happen. Now, same type of overlapping, this molecule or this bond orbital, because this bond is also having the same type of sigma bond orbital. This bond orbital can also do the same type of overlapping another side of the molecule and can show this kind of resonating structure. This is called dancing resonance. Your molecule is not at all having any pi electron, not at all having any plus M group in conjugation, but here the sigma electron are going to take part into the overlapping with the carbocation p orbital, and it's showing a partial overlapping with this and will form this kind of structure. And CPM is so stable that if we give the stability, CPM is found more stable with the benzyl carbocation. Means if we compare with this, CPM is found more stable. So here you can have an idea, dancing resonance is providing, because dancing resonance, because it keep moving, sometime left side, sometime right side. Okay, so that means the stability will be provided by this way, and it is so highly stable that it can be more stable than your benzyl carbocation. So this is a special case. CPM you need to remember, and I hope I'll give you one more example of that and you can get it. Like the molecule, this is the CPM, positive charge, and this side. And similarly, if we are having the benzyl carbocation and this one also. Okay, so which is more stable? Definitely the CPM, because all other system is similar. So likewise, CPM is more stable than benzyl carbocation and highly stable due to dancing resonance. So guys, this is about the stability or the extraordinary stability in the carbocation. In next lecture, we will discuss about the rearrangement of carbocation, which is equally very important topic. So hope you like this video. Please subscribe my channel and hit the bell icon. Thank you.